So good morning and welcome to today's class. Today's class is a continuation of the topic in Form 2, that is structure and bonding. So in structure and bonding, we have looked at ionic bond, we have looked at covalent bond, and now we are going to look at metallic. So this is number 3. We're going to look at metallic bonding. So metallic bonding, usually it is common among metals. So it is a bond between atoms of metals. So bonding occurs between atoms of metals forming a metallic structure, forming a giant metallic structure. So always there's attraction between the valence electrons and the nucleus. So if you have got the valence electrons, that is the electron which is moving randomly within the structure of an atom, then when you have so many atoms joined together, there will be attraction between various nuclei and the valence electrons. So the atoms will look like they are localized, or they are situated in a sea of electrons. And therefore, that is what will constitute a metallic bond, the attraction between the nuclei of the atoms and the valence electrons. So always when you bring atoms of sodium together, many atoms of sodium together, each atom will have one electron. And therefore, when there are like 20 of them, there will be 20 valence electrons that will be moving randomly within the structure of that sodium metal. Those valence electrons, when they are moving randomly, they will be attracted by the nuclei of the 20 sodium atoms, constituting a metallic bond. So each atom nuclei attracts each atom nucleus, that is nucleus attracts the valence electrons. Attract the valence electrons. So this attraction, if you have many of these atoms, is what will constitute a metallic bond. So many atoms of a metal will therefore attract the delocalized electrons hence constituting a metallic bond. So always the metallic bond between the attraction of the nuclei of those atoms which attracts their valence electrons. So that attraction will constitute a metallic bond. So the atoms or the nuclei of the atoms will appear to be immersed in a sea of mobile electrons. So these electrons depend with the atom. For example, sodium will have 1 delocalized electrons, magnesium will have 2, aluminum will have 3. Again, it's also important, we have seen this when we are doing properties of period 3 elements, that in metals generally, when the number of delocalized electrons increases, the strength of the metallic bond also increases. So for that case, you will find that the more the number of delocalized electrons, the stronger the metallic bonds. Hence, the high melting and boiling point of that metal. So you will find, for example, if you have sodium atom, 1 delocalized electron, there's another sodium atom, another one there. So there will be some attraction between these delocalized electrons and the positive nucleus. So those attractions are what will constitute a metallic bond. So this is the positive metal ion. So for example, if this one is sodium, because we are seeing each atom has 1 delocalized electron, then it will be a charge of Na positive 1. Then these are now the delocalized electrons. So you see the metallic ions are like they are immersed in a sea of electrons, and therefore each nuclei will get attracted to these delocalized electrons, which is moving randomly within the structure. So this is what we call a model of a metallic structure. So a model of a metallic structure. So if you have an atom like magnesium will have more delocalized electrons than sodium, and therefore you will find that there will be many of these delocalized electrons. So magnesium nuclei will be massed in a large number of electrons than sodium atom because of that. Similarly, aluminum will have more delocalized electrons, and that is why it will have a stronger metallic bonds. So generally, this is how a metallic bond is formed. And it is also important to know that a metallic bond always occurs when atoms of the same element comes together. Many atoms of sodium element comes together to form a metallic structure. So always there is electrostatic force of attraction that will arise here between the nuclei of this atom and then the delocalized electrons. So the electrostatic forces of attraction So when the pattern of metallic bonding is repeated continuously, you will end up with a giant metallic structure. So we are saying that what constitutes a metallic bond is the electrostatic force of attraction between the positively charged nuclei, which is now this one, they are positively charged, and the negatively charged delocalized electrons. That kind of attraction is what will constitute a metallic bond. So when this pattern is repeated, so when the pattern is repeated, many times a giant metallic structure is formed. So it is important to know that the giant metallic structure will also will arise due to the repetition of this kind of attraction, of this many atoms bonded together in this kind of model. So that is what metallic bond is all about. It is a bond that occurs between atoms of metals, especially if you have sodium metal atoms. Many of them will be joined together by this kind of bonding, forming a giant metallic structure. So each atom nucleus will attract the valence electrons, and many of these atoms, when there are many, their nuclei will therefore attract the delocalized electrons, hence constituting a metallic bond. So the nuclei will appear to be massed in a sea of electrons. So that is how metallic bond is formed. Now, having talked about the metallic bonding, we want to look at some of the physical properties of metallic structures. One is electrical conductivity. So because these ones are metals, because they are metals that are involved in this kind of bonding, we know that metals are good conductors of heat and electricity. So metals due to the presence of the localized electron, due to the presence of the localized electron. So all metals have the localized electrons or mobile electrons that allow electric current to pass through. But this one I've said many times, that the efficiency of conducting depends on the number of delocalized electrons. So the more the number of delocalized electrons, the better the conductivity of metals. So we can say that electrical conductivity depends on the number of delocalized electrons. So i.e., aluminum conducts better than sodium because aluminum has more delocalized than sodium. So when you look at the aluminum metal, it has got 3 delocalized electrons, while sodium has 1. And that's why we are saying that aluminum conducts better than sodium, because aluminum has more delocalized electrons than sodium. So that explains the point of electrical conductivity depends on the number of delocalized electrons. So the more the number of delocalized electrons, the better the conductivity. The better the conductivity. So this can also explain why you find aluminum used in cooking utensil, to make cooking utensil like soporias and cooking pans, because of its better thermal conductivity. Number 2 that I want us to look at is the melting and boiling point. So number 2, melting again, this is something that I remember covering when I was talking about the properties of element across period 3. And we were able to learn that melting and boiling depend on 2 things. One, it depends on the strength of the metallic bond, basically. And this is also something which depends on the size of the atoms, So you are able to see that when the atoms are very small, then there is possibility of them being packed very closely. And therefore, When they are packed very closely, it means that they will have a very strong bonds. And also the strength of the metallic bond also depends on the number of delocalized electrons. So the more the number of delocalized electrons, the stronger the metallic bond, which I've also said in the earlier subtopic. So you will say that generally metals have high melting and boiling points due to the presence So all metals, they have metallic bonds. These metallic bonds are stronger. But again, the strength of these bonds are not the same for all metals. There are those metals that will have stronger metallic bonds than the others. So you will find that the strength of the metallic bonds depends on two parameters, if I may call. The strength of that metallic bond depends on two parameters. So one is the size of the metal. The size of the metal. So just to discuss a little about the size of the metal, when the size of the metal increases, the strength of the metallic bonds weakens. So the smaller the atoms, the closely they can be packed, hence the stronger the metallic bonds, and the stronger the metallic bonds. So when the metallic bonds become stronger, the melting point and boiling point also becomes high. So this is one parameter that affects the strength of the metallic bond, such that when you have smaller atoms, they will be able to be packed very closely to each other, and therefore it means that the nuclei of those atoms will be too close to the delocalized electrons, constituting to a stronger metallic bonds. And when this metallic bond is stronger, the melting and boiling point also becomes higher. Number two, the second parameter that determines the strength of a metallic bond is the number of delocalized electrons present. The number present in the metallic structure. The more the number of delocalized electrons, the stronger the metallic bonds. So, the more the number the delocalized electrons hence they are the melting point. Hence they are the melting and boiling. Hence they are the melting and boiling point. So once you know these two factors, you will be able to know that between aluminum and magnesium, or between aluminum and sodium, which one will have high melting and boiling point. So you can now say that aluminum has high melting point, higher melting point, melting boiling point than magnesium. So when you are looking at period 3 element, we say that aluminum has a small atomic size because of the increased nuclear charge in aluminum metal. That one we learned in period 3 elements. And therefore, there are two reasons why aluminum will have high melting and boiling. The first one is this one. Aluminum atoms are very small in size, and therefore they can be packed closely, and that means they have got a stronger metallic bond. So this is because, or this can be attributed by one, aluminum has smaller atomic size, hence its atoms can be packed very closely, hence thus stronger metallic bonds. So those stronger metallic bonds are what will increase its melting point. Number 2, aluminum contributes more delocalized electrons Aluminum contributes more delocalized electrons into its metallic lattice than magnesium, hence forming a stronger metallic bonds. We have just seen that the more the number of delocalized electrons, the stronger the metallic bonds. So aluminum will contribute 3, while magnesia will contribute 2. So the 3 and the 2, this one will have a stronger metallic bonds than the one with the 2. Again, when now we talk about group 1 elements, just to take you back a little bit to the chemical families, when we look at alkali metals, so here you have lithium, you have sodium, when you look at group 1 metals, the atomic size increases down the group. So that is lithium is smaller than sodium. Sodium is also smaller than potassium in size. Potassium smaller than rubidium. Rubidium smaller than cesium. So it means that the trend of the melting point, melting and boiling points, will decrease down the group. So lithium will have the highest melting point and boiling point. This will have the lowest. This because of the atomic size. As the atomic size increases, the strength of the metallic bond also decreases. And therefore, out of this element, lithium is the smallest one. So lithium will have very stronger metallic bonds than sodium, than potassium, than rubidium, like that. So as the size becomes larger, the strength of the bonds becomes weaker. This explains why lithium have high melting point and boiling than potassium, because of the smaller atomic size. So that's all about the bonding that you are to capture in Form 2. We have looked at ionic bonding. We'll do just a review. We have looked at ionic bonding, and we have said this one is a bond between metals and nonmetals. So a bond between ions of metals and nonmetals. Also, we have looked at covalent bonding. And you have said covalent bonding involves sharing of electrons, amongst nonmetals. And this is due to the fact that nonmetals, they do not want to lose electrons, so they opt to share. Then today we have just looked at metallic bonding. We have said this one involves attraction of metallic nuclei, atoms, and their delocalized electrons. So these are the three main types of bonding that I highlighted in the first lesson of structure and bonding. And so far, so good. We have been able to capture the three of them, and also the properties of the structures formed out of this. We have said that When ionic bonding is repeated continuously, you will end up with a structure called giant ionic structure. So that's the structure that arises when ionic bonding takes place repeatedly. For covalent, we are forming two structures. For covalent, we have got one structure here called molecular structures. We had another one here. This one you said is seen in things like CO2, hydrogen, ammonia, water, etc. Then we also have the giant covalent, or which I also call a giant atomic structures. This one is present in diamond, and we looked into that. Graphite, silicon 4 oxide. Today we have seen that out of metallic bonding, you can form what we call giant metallic structure, which is in all metals, which is present in all metals. So this is just a review of what we have done so far about structure and bonding. So I want us to move forward to the next thing. That is, you want to look at some of the properties of compounds in period 3. In period 3, like the oxides when it comes to structure and bonding. So we want to look at some of the trends. Types of bond across a period, types. Across period 3. So we want to look at the oxides. Oxides of elements in period 3. We want to look at oxides of elements in period 3. So the first one, we want to look at sodium oxide. So sodium is the first element in period 3. And we want to see what type of bonding is in that compound, what type of structure does it form, what is its physical state, especially at room temperature, and how does it react with acids, or does it dissolve in water, something like that. So let's start with sodium oxide. This one is a solid at room temperature. Solid at room temperature. Is ionic. This is an ionic compound, and I remember we did this one during that first class. So the structure here, giant ionic structure, high melting and boiling points. High melting and boiling points. We have looked at the nature of the oxide. These are basic oxide. What do you mean by basic oxide? This is an oxide that dissolves in water to form alkaline solution. So this one dissolves in water And we have looked at this to form alkaline solution. So the alkaline solution will turn litmus paper blue, which turns litmus blue. So that is what you need to know about sodium oxide as an ionic compound having giant ionic structure, high melting and boiling point. It is a basic oxide and it dissolves in water to form alkaline solution. When we look at reaction with acids, this one is a base, reacts with acids to form salt and water. So if you wish, you can write the equation. Let's say plus HCl, sodium chloride, plus water. So how do we balance this? You write 2 here and 2 there. And these are solid, aqueous, liquid. The next oxide that you want to look at is magnesium oxide, which is now B, magnesium oxide. This one is also solid, because it is a white solid at room temperature. It is also ionic compound, just like sodium oxide. Ionic bonding is present there. Then it forms giant ionic structure. Also have high melting and the boiling points. Especially the melting point of this one will be higher than this one. And that one is also because of the size of the cations. The size of the cations. This cation is smaller in size. Magnesium ions are smaller in size than sodium ions. And that's why they form stronger ionic bond than sodium ions. So you'll find it will have high melting point than sodium. Then we have say giant basic oxide as well is also dissolved in water to form an alkaline solution. So dissolves in water to form an alkaline solution. And of course, when we say an alkaline solution, we mean that a basic solution which turns litmus paper blue. Then we also have it reacts with acids to form salt and water. So you will have here magnesium oxide plus, let me use the same acid at HCl for magnesium chloride plus water. So you just write 2 there and it is balanced. So you have solid, aqueous, liquid, which are all neutral solutions. So the next, before we conclude, is aluminium oxide. This one is solid at room temperature. Also will have high melting and boiling. Again, this one is ionic, bonding, giant, structure. This one is amphoteric oxide. Amphoteric oxide, this one we learned in Form 1 that it reacts with both acids and bases. React with acids and bases. So it has got both basic and acidic properties. This can also react with acids to form salt and water. Because it is a metallic oxide. So, when you look at the other oxide, the silicon oxide, those are covalent. Phosphorus 5 oxide, this one. Silicon, oxide, phosphorus 5 oxide, sulfur oxide, then you have the chlorine. All of this one is a solid, this is a solid, this is a gas, this is also a gas. And this one is covalent, 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 covalent. So this is the giant covalent which we have seen. These are simple or molecular, molecular, molecular. So all of them are acidic oxide. These are acidic oxides. So acidic oxides, all of them. So they dissolve in water to form acidic solutions, and therefore their color in litmus paper will be red. So that's the end of that for today's class, and I thank you very much for your attention. Until the next class, thank you.